So basically the gist of the optimization problems are this. If you have a function that models some real-world quantity, we can now find the locations of the absolute maximums and minimums for that function's graph in one variable. Okay. So let's suppose, for instance, we were able to come up with a profit function. Well, we can now find the location, say the profit's given to you in terms of production, right? So if you produce this many widgets, you get this much profit. If you produce this many widgets, you get that much profit. Okay? So if you've got a profit function, we now have a means of finding out how many widgets you should be producing in order to maximize your profit. Or maybe you've got a cost function. And so the same idea holds. We now have a method for finding how many items you should be producing in order to minimize your cost. Okay? There's lots of other applications for this. This is very similar to the related rates section in that if you're not seeing applications that you're particularly excited about, I would encourage you to look at the textbook questions for this section. Because as a lot of story problems go, I never ask students a story problem they've never seen before. Okay? So as a lot of these problems go, I've whittled it down to a handful of questions on here. You'll get a handful more in my math lab, but we just can't cover all of them because each one usually requires you to notice some little trick, and I can't teach you all the tricks in the book. Literally, not figuratively. Okay? So I encourage you to look into the book and see which other problems kind of interest you, because there are quite a few of them. And I'm certain you'll be able to find one in your discipline that you're interested in. Okay? All right. So there's no real new material in this section at all, except for one little theorem that we're going to get to at the end. All right. Or get to on the next page. So we've seen that for a continuous function on a closed bounded interval, we know that it will achieve its absolute maximum and minimum. That's because of something called the extreme value theorem. Continuous function on a closed bounded interval achieves its extreme values. Okay. Then, we've done enough other work to show that we can always find those extreme values as long as that continuous function is also differentiable on the interior. Okay. So, let's talk about these optimization problems. Okay. On the next exam, you're going to have to distinguish between related rates questions, linearization questions, which are going to be in 4.6, and these optimization problems. They're all done a little bit differently, right? Remember with related rates, we differentiated both sides with respect to t. Okay. These are optimization problems. How do you spot an optimization problem? An optimization problem asks you for the superlative of the adjective. What on earth am I talking about? I don't know. I don't know English very well. Okay? So in English, you have the superlative case of an adjective. So it goes fast, faster, fastest, or small, smaller, smallest. That est ending, that's the superlative. Okay? So in these types of questions, we're asking you to find that superlative. So we're asking you to find the biggest, the smallest, the cheapest, the most expensive, the fastest, the slowest. That's how you spot an optimization problem. I might not say find the absolute maximum of this story problem's function. Okay? You'll have to infer that from the questioning. So spend a little bit of time looking for those EST words. That's sort of how you know that you're dealing with an optimization problem. All right. Let's compare and contrast some of the questions we could ask in algebra versus those we can ask in calculus. So a typical algebra problem might go like this. Suppose x and y, or find x and y so that their sum is, let's go ahead and call it 24. Their sum is 24 and their product is 76. That was a nice college algebra question. The equivalent calculus question will say this. Find two x and y so that their sum is 24 and their product is what? As large as possible. That's the largest. I'm asking you for the extreme case there. What am I asking you for? I'm asking you to find the global maximum for their product. Let's look at number 2. A typical algebra problem might go like this. Given this velocity function, What's the object's velocity after 8 seconds? Here's an optimization question. What is the object's velocity when it is traveling the fastest? There's that EST, that superlative. That's how you know you're doing an optimization question. Okay. All right, here's some steps. Okay. In a little while, I'm going to turn you loose on a couple of these problems. Okay. Please, please, please refer back to these steps. Okay. I had people staring at blank pages in my other class for quite a while. So I said, well, what was the first step? And they, draw a picture. They drew a picture, and all of a sudden they could do the problem. Okay? So please, pay attention to these steps. They're not hard and fast. But do know that when I'm grading you, and I'm assigning partial credit, I'll say, did you come up with the optimization function? Check. You get a point. Did you come up with the constraint equation? Check. You get a point. Okay? Did you draw me a picture? Check. You get a point. So those, I will be checking, you're not required to. If you do all correct work and get the right answer, well, you didn't follow my steps, that's okay. But this is how I grade for partial credit. All right. Specifically, what's going to happen as you go through this? Okay. Well, you're going to identify the thing that you're trying to optimize. That goes with the superlative, right? That's the superlative word. Thing I'm asking you to find the cheapest of, the fastest of, the most expensive, something like that. Maximizing profit. Okay? Identify what variable I'm asking you to optimize. Okay? Then you're going to come up with your optimization function. Okay? Ooh, that's kind of hard to see. Then you're going to come up with your optimization function. Your optimization function in this class will often have many different variables in it. And unfortunately, we're not doing multivariate calculus right now. Maybe fortunately, we're not doing multivariate calculus right now. That's for Calc 3. Okay? So we don't know what it means to differentiate a function of multiple variables. We don't know what that even means. Okay? So you're going to have several variables, and you're going to want to get rid of some of them somehow. That's not necessarily a bad thing. Okay? Specifically, somewhere in the question, you'll be able to find something to help you come up with what's called a constraint equation. Okay? Let me just give you some insight into that. If I asked you the question, I'd like everyone to go out, you're all good, it's a competition, I want you to go out and I want you to build the biggest house possible. How big is that house going to be? It's not a very well-formed problem, right? In the real world, we don't expect problems to look like that. Here's a real-world question. I want you to go out and build the biggest house possible, but you can only spend $200,000. I want you to go out and build the biggest house possible, but you've got to adhere to Denver's building codes, and you've got to build it on this 1,000 foot by 1,000 foot plot of land. Okay? Those are real world questions. What did I add to make it a real world question? Constraints, some limitations. We expect those. Well, the nice thing is having those constraints, often in math problems, enable us to eliminate some of the variables. Okay? So you identify your constraint equation, or in the real world, equations, you'll have several of them. And then you try to rewrite your original optimization function, so now it just has one variable. Okay? Once the function has just one variable, then you can find its extreme values using the techniques we've taught. Right? Just for a recap, how do we find extreme values of a function? We identify the critical numbers. How do we find the extreme values of a function? Nope. That's how we found the local maxes and mins. We want to find the global maxes and mins. That was part of finding local maxes and mins. We're finding the extreme values.
Compare the local maximum with the endpoint.
Okay, I'll take that. You're going to take your critical numbers, and you're going to plug all the critical numbers into the function. Then you're also going to plug the endpoints into the function, and whichever one is the highest is the global max. Okay, so folks, it might be worth putting a little flashcard. How do I find global max and mins on one side, and on the back side put those steps? As opposed to how do I find local maxes and mins, in which case I can use either the first or second derivative test. Okay? All right. Then we'll say, answer the question. I guess I should have added that as a bullet point. And you'll see what I mean. Okay? Sometimes I'll say, what should production be to maximize your profit? Sometimes I'll say, what will your maximum profit be? Those are two different questions about the same idea. All right. So this first example is way too easy of an example. I would not put this on a test. Okay? This is way too easy of an example. And in fact, you could actually do this in algebra, because this comes out to be a quadratic. Okay? But it's going to enable us to practice these steps. All right, so let's find two non-negative x and y so that their sum is 24 and their product is as large as possible. All right, for this problem, it doesn't really make sense to draw a picture. Like, this is the only one of today's questions where it doesn't really make any sense to draw a picture. Okay? All right, so the next thing we need to come up with is our optimizing function. Okay? This does have other names. Some books call it the objective function. Some books call it or sometimes I don't know if books call it this, sometimes you'll just hear me call it the max-min function. In all cases, I'm talking about the one that you want to optimize. There's a lot of information up there. Some of it corresponds to what we're trying to optimize. Some of that information corresponds to our constraint. So we've got to learn to suss out the two pieces of information here. What am I asking you to optimize in this problem? Don't say it out loud. Okay, we'll take a look. In this problem, what am I asking you to optimize? Cassidy, what are we being asked to optimize here? The product. Specifically, we want to do what with the product?
Make it as large as possible.
So in terms of our
X and Y.
in terms of our global, what global extremum are we looking for? The global maximum. So we want to come up with our product function and then find the global maximum of it. So you're exactly right. We want to optimize the product here. So how do we find the product of two numbers, x and y? How do you find the product of two numbers? What do I mean by product? No.
Oh, product, I'm sorry.
That's all right. Try again.
Multiplication.
Multiplication. Okay. Folks, if you haven't seen it before, you will at some point. There's a multivariable function. Why is it called multivariable? Because you have to input two things in order to get something out. Does that make sense? Okay. So I've got a question. Why don't I just say, let's let x be 1,000,000 and let's let y be 1,000,000,000, and their product is pretty doggone big? Why can't that be the answer? We are constrained, which is nice because it takes the question out of being open-ended. Right? It puts a little box around our question, our constraint. Okay? So we've identified the optimization function. I can't do calculus on this function right here. Why not? It's got too many variables. Okay? So we come up with the constraint equation. Okay? If you are dead stuck on the constraint equation, just write out a word equation. What are we constrained by in this problem? The sum must be 24. How do you find the sum of two numbers? You add them together. So this would be x plus y must equal 24. This next technique is kind of equivalent to the old substitution technique for solving systems of linear equations that you've seen before. What am I going to do? Well, I'm trying to work with this function. I'm trying to do calculus on this function, but it's multivariate. I want to get it down to just one variable. So what could I do? I could solve the constraint for one of the variables. Which one should I solve it for? In this case, it makes no difference at all which one you solve for. In some questions, there might be a better choice than the other. Both will work, but it makes more sense to solve for R than it does to solve for H, just in terms of how difficult the problem is. But in other problems, it may save you a whole heck of a lot of time, because if I said, find the volume that will minimize your surface area, then V is the one you're after. Okay? So do pay a little bit of attention. Sometimes it matters which one you solve for. In this case, it doesn't, so I'll solve for y, and I get y equals 24 minus x. Keep this little equation here in mind, because if later on you need to know what y is, there's a handy way to find y as long as you've already found x. All right, so now what do? We now return to our optimizing function, but now I'm going to write it as just a single variable x. P of x now is x times 24 minus x. How we doing? Or what did I do? I replaced the y with an expression that's equivalent to y that we got from our constraint. Let's clean this function up just a little bit. We get p of x is equal to minus x squared plus 24. And here you can see why this would make a bad test question, 24x. This is a bad test question because I'm about to ask you for the maximum of this function, but this function's a quadratic. And you learned how to find vertices of quadratics back in college algebra. You didn't need calculus, right? It's at negative b over 2a. Well, now we can go ahead and do calculus. So we're you know, if you're keeping track of my little bullet points, we couldn't draw a picture, bummer. Okay, but then we did this one, and then this one, and now here, or we're in the middle of here, and now we're going to find the appropriate extrema. We're looking for the maximum of this function. What should we do? We need to find our critical numbers, right? So let's find the critical numbers. And I should say something here. Let's say it now. What's the biggest x can be, or sorry, what's the smallest x can be for this to make sense? We said find two non-negative integers, right? So x has got to take on, careful, I'm not going to spend too much time talking about this. X has got to take on integer values. I'm not worried about that. Integer values between 0 and the biggest it can be is 24. Why? Because if it gets any bigger than 24, then y has to be what? Negative. And we said they had to be non-negative. Okay.
Can it be 0?
That's a good question. So I said non-negative integers. So it won't be 0. But we can't exclude that on a domain basis yet.
Can it be 20 or 0 even though the product? Because that makes the product 0.
So we could make one number 0 and the other number 24, and their product would come out to be 0, which isn't very big, but it is a feasible answer, right? It is two non-negative numbers whose sum is 24. It's within the constraint of the problem, even though it won't be the maximum that we're after. Yeah, great question. Okay, so we find the derivative, which is negative 2x plus 24. We set it equal to 0. So that happens when x is equal to negative 24 all over negative 2. Ooh, what just happened? Which is when x is equal to 12. By the way, what is the format of this expression here? It's negative b all over 2 times the a value, right? So you can see how you got that formula for the vertex in college algebra. It's just from setting the generic derivative of a generic, it comes from taking the derivative of a generic quadratic and setting it equal to 0. That's how you get negative b over 2a. Okay, so we've got our critical number. Now what do we do in the process of finding global extrema? The original function, right? So we're going to find p of 12. Why are we finding p of 12? Because 12 was a critical number. What else are we going to find?
P of 0.
P of 0 and p of 24, right? Why are we checking these two? Because they're the endpoints. Okay. So if we plug 12 into the function, where could I plug it in? Well, I could plug it into any expression of that function. I could plug it into this version right here, but what? I don't know what y is yet. Or I could go ahead and just plug it into this version of the function, or this version. Okay? Anyway, when I plug in 12, regardless of where I put it, we end up with 144. When I plug in 0, I get out 0, and when I plug in 24, I get out 0. So where is my global max? Global max. Which, by the way, if I ask for the global min, what's the global min? That's kind of a strange question. Let me say it a little more carefully. What's the location of the global min? The location is at x equals 0 and at x equals 24. Can I have two different locations of the global min? Yeah. But I can only have one global minimum value of 0. There's only one smallest y value on this curve. Of course, the picture that goes with this, here's 24. The picture that goes with this, oops. The picture that goes with this is this parabola right here. Okay. And where's the maximum value on the parabola? We just found it was at 12.
So if you ask, where's the global max at, do we say x equals 12?
Yes.
Okay.
And if I ask you, what is the global maximum value? You say
the y value.
144.
And then if you say, what's the location, is the point? Or...
If I say, what's the location, I'm again asking you for the x value.
Oh, okay.
Yeah.
Gotcha.
Yeah. All right. So, folks, we worked through this, and so what do we, well, wait, I made you write in one more bullet point. Wait, what was that last bullet point? Answer the question, right? I asked you to find two non-negative numbers, x and y. How many have we found? Just x. So we still need to find y. I wish I had an easy way to find y. Oh, I've already solved the constraint for the variable that I had eliminated. So we find that y is equal to 24 minus 12. We get y is equal to 12 too. So here are our answers. The integers are 12 and 12. Not very exciting at all. This is not an exciting question at all, folks. There's a geometric way of phrasing this question. How do you find the area of a rectangle?
By two sides.
Yeah, you take the length and you multiply it by the width. And if I'm trying to, so the product of those two numbers is equivalent to the area of its corresponding rectangle. And what is the most efficient rectangle you could make in terms of area? Uh-oh. Let's have everyone take a minute and read number 5 now. Just want to make sure we understand the question. So what are we doing in this problem? Well, we've got a wire that's got a length of 10 meters. Okay? And we're going to clip this wire somewhere. I don't know where. We could clip it here, or we could clip it here. We could clip it right in the middle. We're going to... Ooh, too far. Oh, golly. We could clip it right here, okay, somewhere. And we're going to take part of it. Make that a little bit more extreme. We're going to take part of it, And from part of it, we're going to construct a triangle. And from the other part, we're going to construct a square. So we are tasked with doing two things here. We are tasked with finding where we would want to cut this wire in order to maximize the area and in order to minimize the area. Okay. So what's hard about this one? Well, what's hard about this one is what's going to be hard about all of these problems going forward. It's not the calculus part. It's coming up with the original constraint and objective functions. Okay. So what's our max-min function? What's our optimization function here? Poof. This is going to take us quite a while. Okay. But we're trying to optimize the area here, right? The area total. I'm going to put a total here, subscript total. The area total. Okay. Well, that's going to come from the area of the square plus the area of the triangle. How we doing? Okay. To make our lives a little bit easier with the numbers, I'm going to let x equal the length of a side of the, and this isn't just any old triangle. What type of triangle did we say it was? Equilateral triangle. Equilateral triangle. Okay, so we're going to call this x, and this x. Okay. And in fact, let's let y equal the length of a side of the square. So we'll call this y, this y, this y, and this y. Okay. So now we can talk about the area total as a function of both x and y. Okay. Well, what's the area of the square going to be? Yeah, length times width, right? So what's it going to be? Everybody? Okay. I'm getting no feedback from some of you. Just trying to double check. Everyone's okay with that? The area of a square, be y squared. All right. Now, the area of a triangle is going to be a little bit harder, right? And normally, how do we find the area of a triangle? We take 1/2 the base times the height, right? What's the base of this equilateral triangle?
X.
We do see that it's x. What's the height? No, the height isn't x. What is the height of this triangle? It's this length right here, right? Yeah, we got our work cut out for us. Let's go find it. Okay, why is it called an equilateral triangle? What does the word lat mean? Side. So all three sides are equal. But what also happens to be a property of an equilateral triangle?
All the angles are also equal.
All the angles are also equal, right? Okay. So if all the angles are also equal, okay, well, first of all, what's the sum of all the angles of a triangle? 180? Okay. How about pi? That tastes a little better, doesn't it? Right? Pi, right? Because what's 180 degrees as radians? It is pi radians. And we've done I have never once used a degree in this class, and so help me, I won't. Okay? That's for engineers. All right? So if all three angles have to add up to pi, then what is the measure of each angle? Pi over 3. So if we look at this, let me just blow this up just a little bit. This is x, this is x. We're looking for this letter right here, which is h, which is height, not hypotenuse. And we construct a right triangle from this. And we know this angle right here is pi over 3, because all the angles are pi over 3. Can we find the missing h? Oh yes. What's the best trig ratio to use for this? The thing we know and the thing we don't know. We do know the hypotenuse of this triangle. What is it? X. And we don't know the height, which is the what side? Opposite. So what's a great trig ratio that uses opposite and hypotenuse? Sine. So we know that the sine of pi over 3 needs to equal the ratio of the opposite over the hypotenuse. Be a little careful. Hypotenuse is x in this problem. So now we can give the height of this triangle. The height of this triangle is just x times the sine of pi over 3. I'm sorry, I've run out of room. Then x times, what's the sine of pi over 3? All right. So we can now give the total area as a function of both x and y, and it's y squared plus 1/2 times x times the square root of 3 over 2, where this is the height that we just discovered. How we doing, folks? This is all problem solving. I don't know how to teach problem solving. I'm sorry. So I just do it for you. Okay, so now let me just take one more step to clean this up just a little bit more. We get the area in terms of x and y is y squared plus the square root of 3 over 4 x squared. How are we doing? Okay, just cleaning up that right-hand expression because it was messy. All right, so there is our objective function. Whew, at long last. Okay. What's our constraint? What are we constrained by? If I'm trying to maximize the area, for instance, why don't I make x be 1,000,000 and y be 1,000,000,000? We only have 10 meters of wire. Okay. So, folks, we need to come up with a constraint based upon the fact that we only have 10 meters. What will our constraint be? What's that? Well, yeah, we're constrained, but what's 10 meters?
4y plus 3x
Equals 10.
The sum of all the perimeters has to equal 10. Well, the perimeter of the square is 4y. The perimeter of the triangle is 3x. So the constraint is 4x, oops, 4y plus 3x has to equal 10. Again, I don't think in this case it really matters which one I solve for. Okay. But I'm going to go ahead and just kind of, keeping with tradition, let's solve for y. So we get that y is equal to 10 minus 3x over 4. Good enough. So now what do? I came up with my objective function. I now found a constraint equation, and what do I do with that? Oh, well, I did, yeah, we solved it for in terms of the variable we want to replace. Now what do? We're going to plug the result of that constraint, solve for one of the variables, back into where? The optimization function. Folks, do practice using the vocabulary on this. If you are good at this, it's not because you somehow know these problems better than other people. It's because you've practiced the vocabulary. You know the steps and you know what each piece is called. Okay? So, the objective function, or the max-min function, now written as a single variable, just x, would be 10 minus 3x over 4 squared plus the square root of 3 over 4 x squared. I think I'd like to, I'd like to clean that up. Let's clean it up. Okay, let's see, this gives us 100 over 16 minus 60 over 16x minus 9x squared over 16. Let's put that x squared out here. That should be plus 9. Plus 9 over 16x squared plus the square root of 3 over 4x squared. Okay. Folks, I FOILed that out in the numerator and then divided each term by 16. FOILed that out in the numerator, and then divided each term by 16. So now we're ready to take the derivative. And when we take the derivative, we get minus 60 over 16 plus 18 over 16 x plus the square root of 3 over 2 x when we take the derivative. Why are we taking the derivative? I forgot to mention that. Because we're looking for critical numbers, because we're looking for global maxes and mins, and for that we need the critical numbers and the endpoints. Okay? Okay, so we're in the process of finding the critical numbers. Notice the derivative is everywhere defined. So we're only concerned with where the derivative is 0. So where is the derivative 0? Well, let's set this equal to 0 and go find out. So we set this equal to 0. That's minus 30/8 plus 9/8 x plus the square root of 3 over 2 x. Set it equal to 0. So this gives us 30 over 8 is equal to 9/8 plus the square root of 3 over 2 x, which is 30/8 is equal to, writing this as a single fraction, this would be 9 plus 4 square root of 3 over 8 x. So what did I do here? I needed this to be 8, so I multiplied it by 4 over 4, and then add it. Okay. So this gives us that x is equal to, we're going to divide, which is the same thing as inverting and multiplying. So we get 30 over 8 times 8 over 9 plus 4 square root of 3, which gives us x is equal to 30 over 9 plus 4 square root of 3. Folks, I need a hand on this. If you would, go ahead and give me a decimal approximation of that. I need everyone that has a calculator to pull them out, and if you don't have a calculator, bring one next time. So we'll just take a decimal approximation of that to the nearest hundredth place, but do round it to the nearest hundredth. Okay, once 2 of you agree on the answer, let me know what you get. All right, I like it. 1.88. Okay. Now, we're after answering this question here. We found a critical number. At this point, this is how we have to answer this question. Okay. We found a critical number. We're going to plug that into the function as well as the 2 endpoints. Okay. So we're going to look at a of 1.88. What's the smallest that x could be? X could be 0. What would that correspond to? Not making any triangle and making all square. Okay. What is the biggest that x could be? Careful. What's the biggest that x could be? What's that?
2.5.
Nope, not for x. It's the biggest y could be. 3 1/3, right? Or I'll just write 10/3. Why 10/3? Because x is the side of a triangle, and I need 3 sides to that triangle, so the biggest I could let each of the equilateral sides be is about 3.33, right? Or 10/3 to be exact. Okay. Ooh. 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 Thank you. Good catch. All right. So, if I can have these 2 tables, if you would plug 10/3 into the function. Okay? These 2 tables, if you would plug 0 into the function, it's not too bad, it's still a little bit of work. And these 2 tables, if you would plug in 10/3 into the function. Okay, once 2 of you agree on the answer, check with one other person and then shout it out. Let's see, where's our area? Here it is. So we got 116ths for these guys.
10
But go ahead and give it to me as a decimal, round it to the nearest decimal place.
The one where we substituted the thing we solved for y for x. Yeah, plus.
Okay, everyone make sure you know what you're doing. Ask your neighbors if you don't. You guys got 6.25? Great. Okay, anybody else? Any other group have theirs? Okay, so we plugged the first one into the area function, right? We got out 2.7, we plugged in the two endpoints in, and we got out these two values. Okay? So, we have a global max where? At what? X equals 0. Okay? So if x is 0, then what are the dimensions of the square? Boy, I wish I had a way to solve for y in terms of x. Oh, right there. When x is 0, right here, when x is 0, what is y? 10 over 4 or 2.5, right? I.e., the square has dimensions 2.5 by 2.5, whereas the triangle has dimensions 0, 0, and 0. Okay? Not a triangle at all. That maximizes your area. Does that make sense as an answer? No.
There's no triangle, right?
Well, but square is the most efficient.
So I guess, I mean, I didn't tell you that it was possible not to make a triangle at all.
Oh, okay.
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 I didn't tell you it was not possible to make a triangle at all. But I'm saying you can cut this wire and you're going to construct a circle and or a triangle and a square. What's the best thing?
Makes sense.
Okay.
But like, if I wanted a triangle, it doesn't make sense.
All right. That's fair. That's fair. So just make it an arbitrarily small triangle and make the rest a square.
Exactly.
Okay. Now, where was our global min? This was at x equals what? 1.88 approximately. So if we do that, we have 1.88, 1.88, 1.88, and the rest goes into making our square, right? So approximately how much is left to make our square if you would take 1.88, multiply it by 3? Then subtract that number from 10,
4.36.
and then divide that by 4.
1.49.
Okay, so then you make the square like this, 1.09, 1.09, 1.09, and 1.09. I think that's a little bit of a surprising result. If we were trying to maximize the area, we made the whole thing into one big square. If we were going to try to minimize the area, some people might argue, oh, let's make it all a triangle, and that's not true. To minimize the area, that's the way you would do it. It's a kind of a surprising result. Okay. I find this extremely tedious. I don't know how you guys felt about this problem. One, this was hard because you had to build a complicated function. But what I find most tedious is this part right here while I'm waiting for you guys to check your endpoints, which is a huge pain. Okay? And I used to make students always check their endpoints with these problems, and it took them forever to get through until I noticed a handy little theorem. Okay? And in fact, I always knew what the answer was, but I still made them check their endpoints anyway. But now that we've got this handy little theorem, it is going to save us some time. So let's look at this down here. Oops. Well, it's all filled in for you. Shoot. All right. Please pay attention, folks. when I make you fill something in, it's because it's a critical part of that definition. Something that I think you absolutely have to understand. So take a minute, fill that in, and we'll talk about it. So let's talk about this theorem. This theorem is basically a way to not have to check your endpoints for almost all of these problems, okay? Which is a huge time saver. In the last example, we got a couple of different answers. One of our answers was an endpoint, but one of them was on the interior. And I'm going to talk about the difference between those two in just a second. Okay? But what is this theorem saying? It's saying as long as you've got a function that's continuous on this interval here, and further suppose that x has exactly 1, and this theorem does not work if you have multiple local extrema. Essentially meaning if you have multiple critical numbers, basically, then you can't use this theorem. Okay? But in almost all cases, during these story problems, you just get one critical number on some open interval. So I'm saying, on an open interval, if you have only one local extrema, and if that local extrema is a local maximum, then it's also a what? Global maximum on the corresponding closed bounded interval. Okay? What this is saying is, let's say we said right here I've got a local maximum. So at some point you'd say it's looking like this. If I'm talking about only one local maximum on this interval, sorry, not just one local maximum, only one local extrema. That's the important part. Is there any way I could ever get up higher than that? No, because what would I have to do to get up higher than that by the time I get to an endpoint? What would I have to do if I'm going this way? I'd have to turn around, and if I turned around, what would I have just introduced? Another local extrema. Do you see that? But if I only have one, then there's no way I can turn back around to make one of the two. So remember, the global maximum can occur where? At local maximums or at endpoints. But if I've only got one local extrema and it's a local maximum, then it's also the global maximum because there's no way I can turn around. That's what this theorem's saying, and I always knew it, but I never took the time to think of it as a theorem. Okay? Our author did. It was very clever of him. Okay? This means that if you're looking for a global maximum on a bounded interval, and you've only got one local maximum, only one local extrema, only one local extremum on that open interval, then it is your global, the thing you were looking for. Okay? So let's look at this problem that we were just on.
So then, is it always going to be like a polynomial?
It doesn't even have to be a polynomial, though. It could be some other complicated function, as long as it's continuous on the open interval. Okay? So let's look at this function right here. This function is continuous where? Well, it's continuous lots of places, but I want to specifically say it's continuous on the interval from 0 to 24. Okay? Then we found how many critical numbers? 1, right here. What is that critical number? A local max, a local min, or neither? Okay, what's the fastest way to figure out what it is? So I could do the first derivative test, right? I could put 1.88 right here, pick test points on either side, right? And if I did that, if I picked 1.88 and picked test points on either side, I would find this is the case, and I'd show that it's a local minimum. But we've already said we don't like plugging points into this messy function, right? So what's a better test to use? The second derivative test. Let's take the second derivative of this function. So where was our function? It's way up here. Here's the let me put that in a different color. Here is the first derivative, right? So what's the second derivative of this function? It would be 18/16 plus the square root of 3 over 2. What's the sign on that second derivative? Positive. Always positive, right? So specifically, a double prime of 1.88 is greater than 0. By saying that the second derivative of that point is greater than 0, what are we saying? We're saying that the function is concave up there. But we already said that that was a point where we had a horizontal tangent line. So by the second derivative test, what do we have? A local minimum. Okay? So x equals 1.88 is a local minimum. Okay? I want to say what? That it's the global minimum. And up until we had this theorem, what did we have to choose to be sure that it was a global minimum? We had to check the endpoints. But since it's the only extrema on the interval from 0 to 24, then it is the global minimum on the closed bounded 0 to 24. It can't be, the global minimum can't be at an endpoint. Okay. How do I know it's the only local extrema? Because I only got what? One critical number on that interval. Okay? So that theorem is a huge time saver. Okay, so the upshot is, I really hope you get some time to get to know that theorem. Okay? But the upshot is, if I'm asking, essentially in this class, now this problem was this first problem was kind of the oddball out, because I wanted us to get a sense of why do we need this theorem. Okay? Generally, if I ask you for a local maximum, and you find just one critical number, I do ask you to show me that it is a local maximum, but then you don't have to do any additional work to tell me that it's a global maximum. Does that make sense? Meaning I'm not going to give you a problem in this class where your extremum for these story problems occur at an endpoint. All right. Let's see here. Let's try this one. All right, Farmer Brown. Oh, this isn't him though. This is backwards cousin. Farmer Norb. Okay. Who keeps llamas, and Farmer Norb's a little backwards, and he's trying to save money, right? Well, his property abuts a creek. Oh gosh, I get Lake Lemon. Banks of Lake Lemon. Sorry, this changes wherever I am, and I haven't changed it for this neck of the woods. You could call it Little Dry Creek, Big Dry Creek. Is that right out here? Big Dry Creek. Okay. His property abuts Big Dry Creek. Okay? So to save some money, what's he going to do? Well, he's going to use the river, the creek, as one side of his pasture. Okay. So he's going to construct a pasture that looks like this. The question is, okay, he's got 6,000 feet of fencing. What are the dimensions that will maximize his area? Now, if he was just building a regular rectangular pasture out in the middle of nowhere, what would be the ideal shape? Everybody, the ideal shape, the ideal rectangle is a square. I don't want that to be the answer, so I change it up. In this problem, I have you use a river as one side of your stream. In the problem before this that we're not going to get to, I have you subdivide it into pens, subpens. Okay? So there's different ways of doing these problems to make sure that the answer is not a square or not a cube. Does everyone see that? Okay. So let's see here. Let's call this x. Let's call this y. Okay, so we've drawn our picture. All right. I'm going to let you guys work on this for a little while. double check.
Yeah, yeah, I did the wrong, yeah.
Okay, okay.
It's like this.
You're doing a lot.
Yeah, I know. I don't even know. No, I only haven't done like last two.
All right, folks. How do we do finding x? You want to talk about any of the work up until then? No one want to talk about any of this work up until then? Okay. Now, I do think you should do this, folks. Do label your objective, do label your constraint. Okay, that's ways for me to give you points. If you just have, because what happens oftentimes, folks, I should show you some of the tests I have to grade. I get 20 different equations there, one of which is right. What do I do? Okay, I don't know if I can give partial credit for that. But if you label which one you're claiming is the objective, then I can give you points for that. If you're labeling which one you think is the constraint, then I can give you points for identifying it. Okay? All right, so then we solve the constraint for one of the variables. Solve the constraint for one of the variables, in this case y. We came up now with a single function of, a function of a single variable, and then we found its derivative, finding its critical number right here at 1500. Okay? Now, x can only take on values between 0 and 3000 if we're going to return a positive area here. Or let me say it like this, if we're going to return a non-negative area, x can only take on values between 0 and 3000. But rather than having to check endpoints, which can sometimes be a pain, in this case maybe not, but in other problems I give you, checking endpoints can be a real pain. Okay? I'd like to somehow use the theorem from the previous page. So I have just shown that we've got a critical point there, and it's the only critical point, let me just say it like this, it's the only critical point on, let me say critical number since that's what I always use, it's the only critical number on the interval from 0 to 3000. So as long as I can show that it is a local, what? Maximum, then I know that it's a global maximum. But do I have to show it's local? Yes. So what should I do to show that it's local? I think the best way to do that is to do the second derivative test. So let's find a double prime of x. Well, a double prime of x is -2, correct? I don't know. I can't.
-4.
Oh, -4. Sorry.
Still negative.
Sorry, folks, I didn't have it in front of me. I was trying to remember. -4. Okay? Which means that if when I take a double prime of 1500, doesn't matter. What do I get? I get a number that's less than 0. So it's concave down. Where on a concave down interval did we have a horizontal tangent line? Right there. Oh. So it's concave down. Where on a concave down interval do we have a horizontal tangent line? Right there. So x equals 1500 is a local max by the theorem. I'll just put by theorem, and you don't even have to write that. It's also a global max. Because there was only one critical number, and it corresponded to a local maximum. Therefore, it's the global maximum on that interval. So in fact, therefore, it's a global max on 0 to 3000. Charlie?
Do you want to include what the value of y would be?
Yes, yes. So at this point, go back to your last bullet point that you had to write in, which was what?
Answer.
We've done all the work, right? You've got it. You've done all the heavy lifting, but make sure you've answered the question. So, what was the question? Give the dimensions and area. Okay. So let's go ahead and find the y value. So I'm going to go back to here. where we found y in terms of x. So we said, okay, y is equal to 6,000 minus 2x. So when x is 1,500, we get that y is equal to 3,000. So the dimensions of 1,500 feet by 3,000 feet will maximize the area at 15 and a bunch of zeros. 1, 2, 3, 4, 5. 1.5 million feet squared will be the area of this pasture. Folks, are there questions on this? Kasha?
How are we finding the interval?
So let me say two things on that. Okay? First of all, you could just say the interval is 0 to infinity, because you know that x can only take on positive values. We can be actually more precise, though, because if you go back to our picture, what's the biggest I could let x be? Well, I always have to have 2x, right? And if I let that 2x consume all 6,000 feet, meaning y is very, very small or arbitrarily small, then x would be 3,000. So the biggest x could be is 3,000. Okay? Yeah, Simon.
For like our reasoning of why the x value was the global
Yes.
minimum, would you be satisfied with me just saying like a prime of x equals 0, a double prime of x is less than 0, therefore x is global minimum?
That would be sufficient, yeah, for what we're doing here.
Okay.
Yeah, so folks, all I need you to do is if you found that there is just one critical number, just show me it is the local of whatever you're trying to find. I do need you to kind of pay lip service to that, okay? But know that, because you know in the real world questions are more complicated. But because checking those endpoints takes a lot of time, I'm content with you just telling me, hey, it's a local max, and you don't even have to say therefore a global max. You just tell me it's a local max, and I'll know that that theorem then applies and that you've done everything I want you to check. Yeah, Charlie.
The area in that should be 45 followed by 5 zeros.
Are you telling me I can't multiply 3 times 15? Thank you, thank you, thank you. Good catch. Amy, was that your comment? Yes.
You
Sage.
don't even have to use all of the fencing to get the maximum area.
What's that?
You don't even have to use because we only use 4,500 feet of fencing
No.
out of the 6,000.
No.
There's 2 X's.
No.
Oh, right. Oh.
Yeah.
I gotcha.
Yeah.
I forgot about that.
In fact,
Okay.
so technically our constraint, I don't really want to spend a whole lot of time on this. There's a whole theory in math called, well, I don't know if it's a theory, but there's a whole topic in math where you do optimization like this. Okay, you actually do it in multiple dimensions. It's kind of interesting stuff. Okay, technically the perimeter needs to be less than or equal to 6,000, but you can quickly make the argument that if you use less than you're supposed to, you can still make it bigger by just making one of the dimensions bigger. So it always has to equal 6,000. The constraint is that it must equal 6,000.
Okay.
Yeah. Let's change that back. Yeah. So we did use all 6,000. Good check. Folks, let's take a break. We'll start up here at 36, please. So let's go ahead and look at question number 12 here now. Okay. So in question number 12, we've got a man launches his boat from point A on a bank of a straight and still river that's 3 kilometers wide and wants to reach a point B 8 kilometers downstream on the opposite bank. He can row at a certain rate and he can run at a certain rate. Where should he land in order to get to point B as quickly as possible? So let's look at this problem real quick. Let's look at the picture that goes with this. So we've got a straight and still river that's 3 kilometers across. Pretty wide river, maybe the Mississippi at some point. And we've got some point B that's down 8 kilometers downstream from the start point of point A. Oh, that's easy enough. Okay. So what's the deal here? Well, this person can row across the stream and then run the rest of the way to point B. Okay. Hopefully you see that if the person is an extremely slow rower and an extremely fast runner, they would probably want to just row straight across the stream, or very, very close. You would never go straight across, but very close to straight across, and then spend the rest of the time running. And if the person was a much faster rower than they were a runner, then they would want to just cut the corner and spend all the time rowing. But depending on how close these two rates are to each other, there's some sweet spot that the person should aim for in order to minimize the amount of time they spend traveling. Okay. Now, this is sort of a silly problem in that, well, two things. Let me first say, though, that the amount of time it takes to compute this problem negates any option that you would take. So in spending the time to compute this problem, you're going to lose out. Okay? So you might as well just aim and go if you were this person. I'm not claiming that. Okay? The next thing is, they actually did some studies, and your textbook has an interesting anecdote about this. Okay? So for those of you interested in animal biology or animal behavior, okay, they did some studies and found that dogs naturally do this. If you got a dog and you throw a ball into the water of a lake or something, the dog will naturally run along the lake for a certain amount of time before jumping in and swimming diagonally towards the ball. And if you were to average out over the long run, on average, they're landing always at the sweet spot. Now, not every single time they do that, but on average, they average hitting that sweet spot. So your dogs are better at calculus than you are. I'm sorry. But that's an interesting fact. How do the dogs know that? Yeah. All right. Well, I mean, yeah, so you make the argument that the dogs that are able to do that survive, and the dogs that aren't able to do that don't survive. So over time, you select for it. Okay.
Just making sure we don't become smart.
What's that?
I was saying, well, like my dog ate my homework. They're just making sure we don't become smarter than them.
Keeping you down, huh?
Yep. That's why I only have a dog.
All right. The other thing is I would argue that this is actually, in one way, one of the most important calculus questions we do, in that billions of people rely on this calculus question every single day. They're just not doing the calculus. Where do we use this question every single day? GPS, Google Maps, route selection is done with this optimization procedure. Of course, it's far more complicated because there are many, many routes from point A to point B, and there are often many, many turns that have to be done along point A to point B, but it is one giant optimization problem where on road A, if you go, this road allows you to go 30 miles per hour, this road allows you to go 45 miles per hour, where should you get on to the faster route in order to get to your destination as quickly as possible? So while you can't compute that problem very quickly, it is being computed for you every day. Zachary?
Oh, that's not a question.
Oh, okay. Any questions on this problem? All right. So this is how we do it. And again, I don't know, maybe you could come up with this problem on your own, but I think it'd take you several hours to answer this question on your own. So I'm just going to show it to you. All right. The time total that you spend is equal to the time that you spend rowing plus the time that you spend running. True? Okay. Then we remember the age-old formula, the distance is equal to,
Distance.
Distance is equal to rate times time. Okay, that's a very old formula. We use it all the time in algebra. Let me just remind you of it. If you go 30 miles per hour for 4 hours, you will travel a distance of 120 miles. Okay? So distance is equal to rate times time, which means that time is equal to the distance over the rate. That's supposed to be a D. It keeps coming out wrong. Distance over rate. Okay? Your time is equal to your distance over your rate. So that means that the time that you spend total is equal to the distance that you row over the rate that you row, plus the distance that you run over the rate that you run. Okay. So if I call this point here, and here I'm not, in this particular problem, I'm not going to do the work to come up with the constraint. To be honest, by the time you've built the objective function, plugging in the constraint's kind of silly, so we'll just do it. Okay? The constraint is that this distance right here plus this distance right here must equal what? 8. The 8 kilometers. But we will substitute in the constraint as we build this. Okay? I don't want to label this x and this y. It's just too long to do it that way. Okay, so what is the distance that you row based on this construct here? That's true, but I'd rather do the distance I row, I'd rather actually calculate it using x. Okay, so what can we see here? Well, because this is a straight river, we formed a right triangle, right? And this side of the right triangle is 3, and this side is x. And so we just need the distance that you row is the hypotenuse of that right triangle, right? So the distance that you row is the square root of the sum of 3 squared plus x squared. That's the distance that you row, the hypotenuse of that triangle. Everyone okay with that? All over the rate at which you row. How fast do you row? I think we said that you row 6 kilometers per hour. Plus, then if x is the distance where you landed, how far do you have to run? So this was somebody who was given this answer earlier. How far do you have to run? You've got to run a distance of 8 minus x. To be honest, I think it's silly to take the time to call that y and then substitute in the constraint that x plus y is 8. Okay? So that's where the constraint of this problem comes in. All over the rate at which you run. How fast do you run? 8 kilometers per hour. Okay. So now we've got our time, the time total as a function of the variable x. So you tell me where you land, and I'll tell you how long it will take for you to do the whole route. So we've got, I'm just going to recopy it. T of x is the square root of 9 plus x squared all over 6 plus 8 minus x over 8. So let's find t prime of x here. Well, let's see here. That's going to be 1 over 6 times 2 times the square root of 9 plus x squared times 2x plus negative 1/8. Folks, I thought of this as 1/6 times the square root of 9 plus x squared, and I thought of this as plus 1 minus 1/8 x. True? Dividing that 8 into both terms on the right-hand side, so when I took the derivative, I just got minus 1/8. You okay with that? Please, 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 stop me if I lost you. There's a good chance, I mean, third of the time this problem shows up on my tests. Okay, so we found the derivative. Now what do we need to do? Find its critical numbers. Okay. Well, it's only critical numbers. In this case, are going to come where it's 0. Okay? So we end up with, let's see here, 0 is equal to x over 6 square root of 9 plus x squared minus an eighth. Where did the 2's go? Okay, they canceled. So we get 1/8 is equal to x over 6 square root of 9 plus x squared. This is the first time we've had to solve a radical equation in a long time. Okay. I recommend the technique of cross multiplication here, although there are many other ways to do this problem. If we cross multiply, we get 6 square root of 9 plus x squared is equal to 8x. We okay with that? Okay. Now, I've got an equation with a square root in it, so I isolate the square root term, done, and then I raise both sides to the index of the radical. Well, this is a square root, so I'm going to square both sides of the equation. Squaring both sides of the equation gives me 36 times 9 plus x squared is equal to 64x squared. Hopefully somebody once taught you, though, if ever you square both sides of an equation, what do you need to do? No? Okay. So let's see here. This gives us the parabola, a messy one. Let's see here. 36 times 9 plus 36x squared is equal to 64x squared. So this gives me 36 times 9 is equal to, subtracting over 36, 28. Right? Yeah, 28x squared. Is that right, folks? 64 minus 36. Am I crazy? Okay, 28. Okay. So then we get that x squared is equal to 36 times 9 over 28. So let's see here. That gives us, so folks, notice I didn't want to multiply 9 times 36 just because I'm lazy. Okay. So at this point, I'm going to go ahead and cancel out like factors. 4 goes into both those expressions. So I get 9 times 9 over 7 is equal to x squared, or 81/7 is equal to x squared. So we get x is equal to plus or minus the square root of 81/7, or plus or minus 9 over the square root of 7 is equal to x. Okay, folks, all I did was solve this equation. I might not have done it the way you would have. Any questions on that, though? So folks, just a lazy thing, when I'm on the board, or frankly anytime, I don't like to multiply big numbers out if I think that I can later work with them through division. So it made sense to wait on multiplying 36 times 9 until I could cancel out some factors with this 28, which is why we ended up with 9 times 9 over 7. Okay. All right. So we've got two critical numbers, but on the interval from 0 to, and here I'm just going to be lazy, and put 0 to infinity. I'm not going to worry. Actually, no, we could go ahead and do this. What's the biggest x could be in the domain of this problem? 8. So on 0 to 8, x equals 9 over the square root of 7 is the only critical number. Okay. So I wish I may, I wish I might. What do we think this is going to be? A local what? What are we trying to do in this problem?
Minimum.
Yeah, because we're wanting to get there in the shortest amount of time, right? Okay, so we're hoping this is a local minimum. What do we need to do to find out that it's a local minimum? I recommend doing the second derivative test on this. So let's go ahead and find, right way up here, t double prime. Okay. See, this is how our derivative simplified. Let's see if I can grab it. Sometimes it lets me do it. Aha! Success. There we go. this was our first derivative. So let's find the second derivative. Okay, so we'll have to do a quotient rule here, right? So we do the bottom times the derivative of the top minus the top times the derivative of the bottom, which is just the derivative of the bottom term. So that would be 6 over 2 square root of 9 plus x squared times 2x, all divided by the bottom function squared. Okay, and I called this f. I should have called it what? What was I calling it before? Yeah, I should call those t prime and t double prime. Okay, so now we're going to look at t double prime of 9 over the square root of 7. Okay. So let's see, that's going to be, what a mess. I'll let you guys check it on your own time. I'll let you guys check this on your own time. What are we going to get? We're going to find that we are greater than 0, so concave up with a horizontal with a horizontal tangent line. So we found what? So x equals 9 over the square root of 7 is a local what? Min. Okay, you don't have to write this part, but I'd like to say it just to keep just to feel like I'm doing my job. Okay? So by the theorem, x equals 9 over the square root of 7 is a global min. Right? How come? Because it was the only local min on 0, or was the only local extrema on 0, 8. Therefore, it's its corresponding global. Now, where the maximum then has to occur is at one of the two endpoints. Which one? You'd have to check to find out where the maximum occurred. Okay? All right, let's see if we've answered the question. I don't feel like we have. Oh, maybe we have. Where should he land in order to get to point B as quickly as possible? Well, let's see here. 9 over the square root of 7. Somebody want to give me a decimal approximation of that?
It is
3.4 what?
0.
3.40. Great, thank you. So about 3.4 kilometers downstream is where you should aim for. Of course, your dog knows that. All right. All right, so from 4.5, I want to go ahead and do question number 10 here. And we commented about this one last time. Do you remember this one? I think I had you all draw some soda cans, right? Same idea here. I guess in this case we've got oil coming in a 1 liter can. I don't think oil comes in cans anymore, but in the olden days it did, I guess. And it makes a nice math problem. So, what type of question is this? This is the first thing you should identify. Well, it says it's from 4.5 optimization problems. Okay, it's an optimization problem. How do you know that in reading the question? It says to minimize the amount of material. It says cost of metal, but if it's all the same metal, then that's the same thing as minimizing the amount of material. Okay? So this is an optimization problem. I'm asking you to find in this case, the smallest amount of material. Okay? Remember we talked about last time those EST words that show up in these types of problems. I'm asking you for the extremum. Okay. How do we do these problems? This is a recap more so of the process than how to do this one particular problem. How do we do these optimization problems? Draw a picture. Great, I like it. Let's draw a picture here. Okay? Here's an oil can. Okay? Let's label some dimensions. And by the way, when you draw a picture, don't just draw, a nice happy picture and draw a fun little label on it or something like that. Go ahead and put your variables on it too. What do you need to be able to describe this cylinder? All cylinders, this is called a right cylinder. All right cylinders can be described by just two numbers. What are those two numbers?
Radius and height.
Yeah, the radius and the height. Okay. You could also do diameter and height, but you need to somehow describe how big the circle is, which we usually do with radius, and you need to describe how tall the can is, which we do with height. Okay. Any questions on that? Okay, we're now going to build two different equations. The what and the what? What do we call them? What's that?
The optimization
The optimization function, and then we'll build also the constraint, right? If I said make a can of oil that's going to minimize the amount of material it takes to make it, why don't you make one really, just about that one right there? Why didn't that work? Because it's got to hold a liter. That's my constraint, right? I'm constrained by the fact, in the process of minimizing the material, I'm constrained by the fact that it must hold a liter. Okay? So in fact, let's go ahead and say that we are constrained by the fact that the volume must equal 1 liter. Okay? How do we find the volume of a cylinder? I do expect you to know this.
Pi squared A.
Yeah, how do we think, how do we think about that? The base of the circle, the base of this column times its height, and in this case the base is a circle. Okay, so these are called prisms. In this case, I guess you'd call this maybe a circular prism. Okay, and for these prisms, you just take the underlying base and then cross it with a third dimension. In this case, the height. Okay? So when I look at this, I just think of, I've got this circle right here, and I just stretch it up by a factor of h. That gives me a three-dimensional object. So what's its volume? It is the area of the circle, pi r squared, crossed with the third dimension. Area times height equals volume. So we get L. Oh, 1L. I want to say this, though. A liter is a perfectly fine measurement of volume, but it is itself just it's liters are raised to the first power. It's already a unit of volume. And I want to think of it as being a product of three dimensions. So what is a liter equivalent to?
1,000 cubic centimeters.
Yeah, a liter is equivalent to 1,000 cubic centimeters. Okay, if you don't know that, that's okay, I'm telling you. On a test question, I would go ahead and just say that this volume is 1,000. I won't mess with the units with you on a test question. Okay, but my math lab will at times, so we're practicing that. Okay. For those of you who don't know, 1 liter is equivalent to 1,000 milliliters. That part you should know. And then what is a milliliter? A milliliter is 1 cubic centimeter. So if a liter is 1,000 milliliters and a milliliter is a cubic centimeter, then a liter is 1,000 cubic centimeters. All right. So this is our constraint. And then MC said, oh, we've also got to come up with our objective function. The thing that we're being asked to optimize. What are we being asked to optimize here? What do you say, Haley?
We're asked to minimize the material or
Material, or we can think of that as surface area, right? The material that comes up as a surface area. All right. When you do these problems about material, I recommend you think of trying to wrap a Christmas present, but not as you wrap one nicely. Think of how Mr. Von Toggen wraps his Christmas presents, because he's lousy at it. If I wanted to wrap this can, you know what I would do? I would cut out a circle, and I would glue it to the top. And then I would cut out a circle, and I would glue it to the bottom. And then I would cut out something to wrap around the side and glue it to it. Okay? That's how I want you to think of doing this. If you think of it that way, then you'll be able to come up with the formula for the surface area of a cylinder. That's, again, something I ask you, I think that that's fair to ask you to deconstruct that. I'll show you the process. Okay? So what did I say? I said, oh, I want, for the material, which will be a function of both R and H, I said, oh, I want one circle right here that I'm going to cut out and I'm going to glue to the top, right? that circle can be described by just the radius, right? And then I want one for the bottom, right? Then, at this point, what is still left to be wrapped? Oh, very good. Very good. Okay. Let's talk about that. I want to talk about that just a little bit more. At this point, I've taken care of the top and bottom of this can, so I'm left with a sort of a tube with no top and bottom. Okay. What could I think of doing? I could think of taking a scissor and cutting it along like that, right? And then in your head, if you could imagine, I cut along this tube and I unfold it. What type of shape do I get? I get a rectangle. Ooh, that's a little weird. I get a rectangle. Okay? And what do I know about this rectangle? Well, I cut along this dimension here, which was this line right here, so what's this dimension? It's h. And then, what do I have to do with this? I've got to wrap it around the circle. So as Amy said, how long is this?
Circumference.
It's the same as the circumference of the circle, right? How do you find the circumference of a circle? It's 2 pi r. Okay? Folks, I will not give you, if this question showed up on a test, I won't give you the formula for surface area. I won't give you the formula for volume. If you've dead forgotten, I'll give you the area. If you come up to me and ask me, I'll give you the area for the formula for a circle. If you've forgotten circumference of a circle, I'll give you that. But from those two pieces, I expect you to be able to deconstruct this cylinder and then come up with the surface area formula. Stop thinking of formulas as these mystical expressions that somebody came up with. They're built from very basic principles most of the time. Okay? All right. So what is our surface area? It's going to be 2 pi r squared. What does that take into account? It takes into account this circle and this circle here, right? Plus, how do I find the area of this? What do you say? Chandler, how am I going to find the area of the tube part of the cylinder? Yep, exactly. Exactly, so what would it be? 2 pi r h. Great. Okay. There's our constraint problem. So what are we being asked to do here? Well, we're being asked to minimize the what? The material. So I need to come up with the material as just a single function, or excuse me, a function of a single variable, right? I can't do calculus on that expression because it's got too many variables. So what do I do? What's my next step? What do you say, Jigme?
You have to substitute you have to get rid of one of the variables.
Yeah, we gotta eliminate one of the variables, and how do we usually do that? What do we usually go to? Go ahead. You go to the constraint function. So we're gonna go to this expression right here. Okay. I don't know if you want to call it a function or equation, I don't know. But you're gonna go to that constraint function or constraint equation right there, and you're gonna solve for one of the variables. Sometimes in these problems there will be a best choice. Like if all you were ever after, if the problem said give the radius that will minimize the amount of material, then there's a clear choice. You definitely want to get rid of h. Or if it said find the height that will minimize the amount of material, then there's a clear choice. You want to get rid of r. So you'd solve for r. But when there's not a clear choice, you want to pick whichever one's easiest to solve for. Who's easiest to solve for in this problem?
We don't want a square root. So.
Yeah, I don't want to introduce a square root here, so let's go ahead and solve for h. So this gives us that h is equal to 1,000 over pi r squared, dividing this pi r squared over to the other side. So at long last, we can write the amount of material as just a function of one variable r. It would be 2 pi r squared plus 2 pi r times 1,000 over pi r squared, right? I can't remember. I got distracted by this symbol that showed up. Okay, great. I can take one more step to clean this up. And as we've always seen in this class, it's easier to clean up your functions before you do calculus with them. that's our objective function, now written as a function of just one variable. Okay? So now that I've got this, what do I want to do? Now we're ready to do some calculus. This whole problem, this whole real-world problem of coming up with the dimensions so we use the least amount of material possible constructing this oil tin is really just a find the extreme values of this function problem. Specifically, we want to find the absolute minimum of this function. So, let's go ahead and give that a shot. Okay. The smallest r could be is 0. So notice that this is, so let's say just minimize this. On the smallest r could be is 0. And technically, what's the largest r could be? It could become infinitely large because if you're going to have a volume, you can't derive it infinity, but it can become you can make it as large as you want, because if you're going to have a fixed volume of a liter, you just make the height very, very tiny times whatever the size of your circular base is, and that ensures that you can still get to 1,000, right? So you could still always get to 1,000. So there's no upper limit on what your radius could be for these cans. Okay, so we want to minimize it on this interval. So here we go. We take the derivative, because we're looking for the critical numbers. So here's the derivative. Here's the derivative. It is 4 pi r minus 2,000 over r squared. We're missing adding. Any questions on how we did that? Anyone have any questions about that derivative? So I thought of this as 2,000 r to the minus 1 power, right? And then I did my power rule and put it right back down. Okay, any questions? Okay, so I set this equal to 0. Let's take the 2,000 r squared over to the other side. So we get 2,000 over r squared equals 4 pi r. Doggone it, an equation with fractions. Let's get rid of the fractions. We're powerful mathematicians. How do we get rid of fractions? By multiplying by the LCD. Right? So multiply both sides by r squared. We get 2,000 equals 4 pi r cubed. We can do that because r can't ever actually be 0. Divide both sides by 4 pi, we get that r cubed is equal to 500 over pi. Don't let your eyes glaze over. Don't pick on this number, it's going to be ugly. Okay? But it's the one we want. We get r is equal to the cube root of 500 over pi. Just to give us a dimensional, just to give us a sense of the size of that, if somebody would take the, give me a decimal approximation, was it 5.419? We'll call it 5.4. Just, I mean, that's fine. I like that you gave that far, but let's just leave it at 5.4. Just to give us a, 5.4 what? Centimeters, right? Just to give us a little bit of sense of size now. So whenever you see this ugly number here, if you want to think about them as 5.4, you can. What's that? Well, that's the radius, though, right? Not the diameter.
Oh, right, yeah.
Yeah. So that's a good size for a 1 liter oil can.
Yeah. 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 I mean.
Think about your Nalgene bottle. It's about a liter.
Yeah. Yeah.
It's not the ideal size either, though, because they want you to hold it in your hand.
Yeah.
Right. All right. All right. So that's our radius. Where we have a what? All we know so far is this is where we have a what? We don't even know it's an extremum. We don't know it's a min or a max. All we know is that it's a critical number, right? Now we only got one critical number, so we're feeling pretty comfortable, right? What do we need to do? All we need to do is confirm that it is a local minimum, and if it is, then it will also be the Global minimum. So all I have to do is confirm that this is a local minimum. To do that, what do I have to do? What do you say? What do you say, Abby?
Wait, we're confirming that it's a local minimum.
Confirming that it's a local minimum. So we've got two possible things we could do. The first thing we could do is the first derivative test. What's the second one?
Second derivative?
We could do the second derivative test. Okay. Which one would you like to do? Yeah, hopefully you're learning that for these nasty story problems where the numbers aren't nice, it's a lot easier to do the second derivative test on them most of the time. Okay, so let's find the second derivative. M double prime of r should be 4 pi plus 4,000 over r cubed, I think. Let's check that. I can't remember. Yes, 4 pi r, so that'd be 4 pi, and then plus 4,000 over r cubed. Any questions on that? So how did I do that? I went back to the first derivative, and I just thought of this term right here. I thought of as minus 2,000 r to the minus 2, and then I did my power rule on it, right? So I brought down the minus 2. That's how I got plus 4,000. Subtract 1 from it gives it minus 3. Take that minus r to the minus 3 down below the line. Okay. Now we found the second derivative. Great. How do we actually apply the second derivative test? Yoshin, what should I do? So we found the second derivative.
We already find the second derivative.
Mm-hmm.
And just make sure they are like less than 0.
Yeah, so we're looking, well, actually, because we're looking for a global minimum, we're actually hoping that it's going to be greater than 0 because we want it to be concave up, right? So how do we check that? We simply take our critical number right here and plug it in, right? Well, we get m double prime of the cube root of 500 over pi. Well, what's the sign on that? Don't work too hard, folks. 500 is positive, pi is positive, so their ratio is positive, so their cube root is positive, so I'm plugging a positive number in for r. This whole expression is going to be positive. Notice that's the beauty of doing the second derivative test on these story problems. Generally, it doesn't require much of an argumentation to show what the sign of the second derivative is. Okay. Why did I check for the sign of the second derivative? What's the logic there? What do you say, Kasha?
To find the minimum,
How does that tell us it's a minimum?
because it's a local minimum, therefore a global minimum.
That's true. You're doing the last two steps, but I'm missing a step in between there. How do we know that that's a local minimum?
Because if it's greater than 0, it's concave up.
If the second, so let's be a little careful with our pronouns. If the second derivative is positive, then we know that it's concave up. But what did we also know about this r value? So we know this tells me that it's concave up on the function right there. But there's lots of places along this concave up interval that we could be talking about, right? How do I know that it's the minimum of that interval?
That's where the first derivative is.
Yeah, we set the first derivative to be 0 there when we found that r value. So we also know that it is a place where we have a horizontal tangent line. So while there are many potential places on a function that it could be concave down, there's only one place where you are concave down and have a horizontal tangent line, and where is that? Right there. So it is indeed, you don't have to worry about writing that out, but that's what the second derivative test is telling you. That's why to do the second derivative test, you find a place where the first derivative is 0, and then just check its concavity. And as long as that concavity is not 0, you can make a conclusion. Okay. So, oh yeah, Haley.
This is just kind of like a general question.
Uh-huh.
Like, what would be the best, like, kind of question, I guess, in your opinion, that would work for, like, the first derivative test?
Yeah, that's a great, yeah, that's a really good question. So we have these two derivative tests. Why did I give you 2? Just give you more things to juggle because you don't have enough. No, that's not the answer. Okay. Why did we give you 2? Well, different ones are applicable to different scenarios. I find that when it comes to graphing the entire function, I like to do the first derivative test in the chart that we do because that helps me with graphing the rest of the function. It gives me the intervals for increasing, decreasing, besides telling me whether I've got a local max or local min at a point. Okay. But for the second derivative test, I find that that's faster when I just want to know about one bit of information, just what is going on at this one point. It's usually faster to check with the second derivative. So the short answer is, when I'm doing my graphing problems, I usually use the first derivative test. When I'm doing my story problems, I generally use the second derivative test. That's not quite, I don't know if that's a hard and fast rule, but that's generally what I do. Yeah, great question. Great strategy question. All right. Okay, so R equals the cube root of 500 over m, or excuse me, 500 over pi, is a local min. That's far enough for me. That's all you have to tell me. Okay? Just to reiterate, there's some more explanation going on here. Okay? The additional explanation is, since it was the only local extrema on 0 to infinity, it's also the global min on its domain. That's the extra step that tells us that we've actually found the global min. I don't require you to write out a statement like that. I feel like it's just a little bit too complicated. And if you've gotten to that point in the story problem, I'm satisfied. Okay? But what do you have to do? You can't just find a critical number and call it the answer. You do have to show that it's a local of whatever it was I told you to find. I do require you to pay lip service to that. Okay? To be honest, folks, if you take the second derivative like I did, and then you plug in the number, then just write out, to be honest, just write out whatever that's, just write out what that's supposed to be. You know you're looking for a local minimum, so you know it needs to be concave up, so just put greater than 0. I won't know that you didn't actually check it. Right?
We don't have to put the, like, what that equals?
Well, I mean, you don't actually have to find, I don't require you to find the number, right? I don't ask you to find the value of the concavity. I just ask that you check the sign on it. But if I'm asking you to find a global minimum, it's going to be a problem that has a global minimum to it. So it's going to have the local minimum at that location. So this is never not going to be what it's supposed to be. I don't do that to you. The only problem where you saw where this didn't happen was that wire problem that we did at the very beginning. Okay? And that was when we looked for the maximum for the wire, the square was best, which was at one of the endpoints. All right. All right. So did we ATFQ, did we answer the question? No, what was the question? Give the dimensions, right? Okay. So we found the R value. We found the R value that's going to give us the global minimum, but what else do we need? The height. Boy. Oops, I didn't do it here. Where is it? Boy, I sure wish I had an equation for H in terms of R. Boy, I sure wish I had an equation for H in terms of R. Oh, I will have always done that in the process of solving for the constraint, right? Okay, so let's see, 1,000 over pi r squared. Oops. So we get that H is equal to 1,000 over pi times the cube root of 500 over pi squared. If you want, you could get a decimal approximation of that, but it's not required. There's the exact answer. I'm satisfied with parking it there, except for what? We should probably put centimeters on here and centimeters on there. Did we find the two dimensions? Yes. We've answered the question. Okay. Now, it could be on a problem like this, I might say in the question, I might say, what is the minimum surface area? That'd be kind of mean for this one just because the numbers are so nasty. But what would you do in that case? You would actually take your M your R and your H, and you would go back to here and evaluate and figure out what is that minimum surface area. I'm saying that just because two questions can look pretty doggone similar, but what I'm asking for the final answer is slightly different in them. Okay, there's that. So there is, you will have a video up shortly. Let's see, we did this one in class. You'll have a video up shortly that does these two, number 16 and 17. Okay, actually the video's already up for that. You could already watch the video on that. I'm gonna make a new video that puts all these together, but the video's already up for how to do 16 and 17. Okay. So I would watch that, because those are definitely fair game questions here. All right. I want to now jump back to section, 4.9. Do I have it? I guess I don't have it yet. Let's stop this.